Welcome to The Explainer. Today, we're tearing into the architecture of the PTSG core. That stands for Programmable Timing Sequence Generator. It's a minimal, instruction-driven core that fundamentally changes how we think about hardware design. Look, if you've ever felt completely overwhelmed by the tangled, messy logic of traditional hardware design, you are going to love this. This core introduces a really elegant solution by taking what is basically a conceptual cleaver straight to the fabric of time and space. So, picture this. You're building a hardware controller, right? And your finite state machine, your FSM, just starts growing completely out of control. It literally becomes this massive web of conditions and timers. It's a classic engineering dilemma. Usually, your alternative is to just drop in a general-purpose CPU, like a soft-core processor. But come on, that eats up massive fabric resources and introduces a complex memory hierarchy you simply don't need for basic control tasks. So, how do we actually solve this state explosion without all the bulk of a CPU? Well, that is exactly what the PTSG architecture answers. Here is our quick roadmap for the explainer. First, the FSM mesh structure problem. Next, the complete separation of time and space. Then, independently operating mechanisms, followed by a clear comparison of PTSG versus FSM. Finally, we'll wrap up with real-world peripheral control examples and the amazing AI code generation accuracy boost.
All right, let's jump straight into Section 1, the FSM mesh problem, and why it's such a structural dilemma.
You know the drill with conventional finite state machines. Time and state, they are completely, hopelessly entangled. A single state in a typical FSM diagram is trying to represent two different things at the exact same time. It's saying the system is in this specific configuration and the system is at this specific point in time. And because these two entirely different concepts are glued together, your states just multiply. They create this massive cognitive bottleneck that grows super linearly. Think about what happens when you just want to insert a long wait into an FSM. You end up accumulating all these useless intermediate placeholder states. And when you need to express complex parallel timing relationships, forget about it. The whole diagram turns into a nightmare, mesh-like structure of overlapping transitions. The cognitive cost is just huge. As a designer, you are literally forced to hold potentially dozens of interacting states in your head simultaneously. It is visually and mentally exhausting. Moving right along to Section 2, time and space separation, which is the core philosophy of PTSG. Here is the absolute game changer. PTSG basically takes a meat cleaver to those two dimensions. The time axis is managed exclusively by state instructions and intervals. The space axis, meaning your logic and configuration, is managed entirely by state transitions, like branches and jumps. And the beautiful part? These two axes never mix. A state instruction doesn't change your state number, and a state transition doesn't implicitly make the system wait. This means you can reason about your timing and your logic completely independently. There's this quote directly from the architectural specification that I absolutely have to share because it just perfectly captures the whole philosophy. It says, time on the state axis, space on the state axis, condition outside the core, intelligence in the dialogue. It's almost poetic, right? By cleanly isolating these elements, the architecture just becomes incredibly sharp and focused. Let's peek under the hood in Section 3, independently operating mechanisms. So, how does this actually work mechanically? It's basically a simple three-step dance. Step 1, you have a state counter that counts down durations. That handles the time axis. Step 2, while that clock is ticking down, the state number register holds perfectly steady. It doesn't shift just because time is passing. That's your space axis staying locked. And Step 3, when a branch or jump instruction executes, it updates the state number. It shifts space without inherently consuming any extra time. It's a beautifully decoupled internal mechanism. Now, to keep this whole machine running fast and lean, all conditional complexity is externalized. I mean, all of it. PTSG accepts just a single 1-bit condition input. External logic handles all the messy stuff out there in the fabric, threshold tests, sensor processing, multi-signal and/or logic, and boils the whole shebang down to a simple 1 or 0 for the core. By drawing the boundary at just 1 bit, the core avoids all that nasty feature drift and stays hyper-focused on its real job, time and state. Which brings us to Section 4, a clear comparison of PTSG versus traditional FSMs. Look, trying to read a traditional FSM is basically like trying to solve a giant graph problem in your head, tracing arrows all over this tangled web. But PTSG, it creates a simple, straightforward, linear sequence.
Because time and space are separated, you just read sequentially down the list to see what happens, and you simply track the state counts to see when it happens. The effects are totally localized. This drastically reduces the visual and mental complexity of your design. To put it exactly how the source material does, inserting a long wait does not add states to the instruction list, it adds a single stay instruction with a large counter value. Honestly, this completely flips the script on how you design hardware. You are no longer managing an entangled mesh. You are managing clean, easily separable sequences and intervals.
Let's make this concrete. Section 5, real-world examples of peripheral control.
So this architecture enables this brilliant concept called background execution, and it is an absolute lifesaver for most peripheral interfaces and control protocols. In PTSG, right before a stay begins, you can issue global commands to set up an external register. Then, during the stay window, while the core is just holding the timing signals required by the external protocol, those background commands actually execute. So by the time the stay completes and the next state begins, your external write is already totally finished.
This is a huge, huge win for hardware efficiency. That wait time, you were going to spend it anyway holding timing signals for some peripheral protocol, but now it's actually reclaimed as computation time. It literally folds parallelism directly into your time series. And it does all of this without adding a single extra state to your count and without requiring you to build separate parallel hardware that just eats up your precious FPGA fabric resources.
And that leads us perfectly into Section 6, the strategic advantage of AI code generation.
Get this, it turns out this entire architecture has an inherent AI affinity. Because the 32-bit instruction word is so stripped down and minimal, it actively prevents large language models from hallucinating. I mean, it only uses 4 out of 16 possible opcodes. It features a completely uniform bit assignment, so the AI doesn't have to memorize crazy complex layouts. Complex conditions are externalized, and unused opcode slots are strictly locked down to contain any future feature bloat. All of this makes it remarkably easy for an AI to generate flawless hardware control code. Because we made that fundamental choice to separate time and space right from the start, AI agents don't have to untie that awful tangled FSM knot. As the spec points out, they don't have to solve what is the state-time relationship at this point. Instead, they can just read the stay durations and state transitions as two clean, completely decoupled streams. It's basically spoon-feeding the AI the exact format it digests best.
So here's what I want to leave you with today. A fascinating question to ponder. If we give AI these crystal clear, completely decoupled streams of time and space, what entirely new horizons of automated hardware design are we about to unlock? The PTSG core proves that by radically simplifying the foundation, we can build vastly more capable and easily generated systems. Thank you so much for joining me, and I hope this gave you a fresh, exciting perspective on tackling hardware complexity.